Okay, good afternoon. We are now ready to start more than one particles. But before that, let me ask you questions on what we have done so far, if you have. Things that you would like to see again, which are not particularly clear. Use this occasion. Which part? I mean, the use of the derivation itself. I mean, from the sign going towards a delta function. Is this?
And where we should have continuum and this. There was an explanation on the part of on the continuum and discrete states and the conservation of energy on that part of the final.
Yeah. Okay. I was just trying to tell you that in general there are two possible situations when you might want to calculate a rate. The first case is when you have a discrete spectrum and you are calculating the rate for absorbing, for instance, and going from some initial state to some final state. In that case, if you use the expression with the delta function, somehow you are overdoing it. You are really requiring a very infinitely sharp energy conservation requirement. Okay? So in other words, the delta function would have something like E final minus E initial minus h bar omega, where omega is the period of the frequency of the perturbation you are applying. And this obviously will give you zero rate if omega differs even infinitesimally from the energy difference. Now, this is not true, in fact. Systems do absorb even if you differ a little bit from the right thing. Okay? In other words, this curve has a natural width in some sense. Okay? And therefore, it's not wise to use, in particular, this form. Perhaps a better idea would be to use the sine square. Okay, remember that we had an expression involving the sine square of omega. What was it? Omega fi minus omega divided by times t divided by 2. Okay, divided by something like omega fi. I was using ni, but now I'm calling the final state f, so that you understand that this, okay? Minus omega divided by 2 square. Things like this, okay? I forgot if there were extra factors, but I think that these were, well, to get really to the delta, you need a pi t here, okay? So the correct expression would have something like this, divided by h bar square, and then there was a pi t that you insert here and there in such a way that this is an object. Do I remember correctly by heart? Let me see the correct factors. Yeah, it's quite perfect. Okay? So this is the probability, okay? Obviously in first order, and neglecting non-resonant terms, that you excite your system from I to F, 2 levels. Okay? Now you see that this is not zero, even if this doesn't exactly match omega fi. Omega fi, by the way, is this quantity divided by this divided by h bar. okay? So even if this is not 0, this is still a finite quantity, so there is some width, okay, in frequency that the system can have. This width depends on time. So the larger is t, the finer is the width, but the width is never 0, really, okay? So if you have to calculate a rate of this type, you better use an expression like that. In the end, what is important, well, this is the probability. Then the rate we discussed is the probability per unit time. So you divide by t. So you divide all these things by t, and you get the rate for going from I to f in first order. Okay? And so this disappears. So we discussed that this is the expression in the limit in which t becomes very large. Then this would approach almost a delta function, but you should better use the delta function expression when you are really willing to sum over many, many final states. In fact, over a dense spectrum of final state, okay? In that case, essentially, what you have in mind is that you want to have the rate for going to a certain final energy, okay, where in every single small window, many, many levels will contribute. And on the assumption that the matrix element will be only depending on the energy and therefore will be roughly identical for all those states, okay? What you have is essentially that you have to sum over all the delta functions, okay, which are associated to those levels. At this point, the process is totally identical to calculating the number of levels, okay, in a certain energy intervals, which is called the density of states, okay? So that's the reason why this is somehow useful when the question about the width is not important. There are so many levels, in fact, a very dense spectrum in the thermodynamic limit of levels that you really want to know the density of states there. And therefore, the delta really is integrated over energy to produce a density of states, okay? So this is what all I wanted to tell, nothing.
And how does that matrix element affect the probability?
That's the point. I mean, if the matrix element varies wildly between a given state and this neighboring state, then there is nothing that you can do in general, okay? But suppose that the matrix element is really only, I mean, smoothly depending on the energy that you are going to look at, then what you can do is, in principle, what you should do is to sum, okay? Suppose that I have a certain range of final states that I want to calculate my rate to, okay? So I have a certain final energy, EF, and I allow myself a certain plus or minus delta E over 2 of width, okay? So I want to sum this thing, sum the rates, so sum the rates for going to the final states over all F such that EF is in the window, well, how did I call it EF. Let me call it EF bar. EF is in a certain window, EF bar minus delta E over 2, EF bar plus delta E over 2, okay? This is what I want to calculate, all right? Now, this is nothing but the sum of essentially these terms, okay? now, there are two sources of dependence on the final state. One is through here, okay, and through, therefore, this factor. And another is through here, okay? So, if essentially this is very grossly speaking constant over all those states, remember delta E is small, okay? Then I can take it out of the sum and say that this is just VFI square, obviously for the energy E bar F, okay? So let me call it F bar, I mean the average thing, over H bar square. And then I have to sum over all final states, so over all things, such that EF belongs to this interval here, okay? EF bar minus delta E over 2, okay? So what I am summing now is these factors. But assuming that T is very, very large, this is essentially an object that is approaching a delta function, okay? So in the limit in which the spacing and everything is so small, this sum also approaches an integral, okay? If you put the appropriate factors of volume, we discussed this thing when we discussed the plane waves, how to normalize them, okay? So by this very similar tricks, putting factors of volume, you can transform the sum into an integral over the energy. But then, so over the energy over this interval, EF bar minus dE over 2, EF bar plus dE over 2. But then the delta, okay, is simple, right? Because what's the integral of a delta? If the EF is inside the interval, is 1, otherwise it's 0. So in some sense, this is a device to count, okay? So you see that immediately this gives you the number of levels. This object gives you the number of final states whose energy, EF, is in the right interval, so less than EF bar plus dE over 2 and greater than EF bar minus dE over 2, okay? So the number of final states in a given interval, okay, is essentially, apart from the width of the interval, the density of states. So this is the concept I wanted to communicate, nothing else, okay? So, I mean, in practice, you need to, obviously, if you need to calculate something, to put the factors, the volumes and things so that things make sense. But what is behind is nothing but that counting how many levels there are. And you know that this is something that, I mean, always occurs. When you have a free gas of, for instance, of fermions, okay? So you have your dispersion k square, right? K square. H bar k square over 2m. And this is k. Suppose that we are in one dimension. Then, if I discretize the system in a certain volume of, well, let me call it L, okay? So 0L. And then I impose what are called periodic boundary conditions, for instance. You know that the k vectors that are allowed are not all of them, but just the discrete values k equal to 2 pi over L times n, where n can be any integer from minus infinity to plus infinity, okay? So this fine mesh of k's that are just 2 pi over the size of the box that you are considering, and becomes smaller and smaller as the size goes to infinity, okay? Now, if I want to count the number of levels that there are in a certain energy interval, I must notice, for instance, that since the curve is going kind of flattish here. There are more levels in this energy interval here than in the same energy interval up there. Okay? So if the spectrum was linear, okay, like this, for instance, which happens, for instance, for acoustic phonons, then the number of levels that you find in a certain energy window is constant as you go up and down in energy, you realize, right? But here, no. In particular, here you find less, in this certain thing, you find less number of levels here than here, because many more accumulate, right? And so you expect that the density of states in this case will be not a uniform thing, but there are more states going down in energy. And indeed, you can calculate there is a 1 over square root singularity of the density of states there in 1D. In 2D, it would be flat in 2D, because in 2D there is another axis, and therefore, well, if you account for the element of area in the integral, you will see that there is indeed a correction of this 1 over square root into a constant. And in 3D, the element of volume even further reduces the density of states, and you get something like this, okay? Square root of the frequency. So this counting of the states is quite common in many problems, okay? And sometimes also you have to account for them in calculating the rate, okay? So for instance, the rate to excite an atom to some excited state, where the conduction electron, where the electron goes away, has to account for the density of states that you encounter out, okay? So if there are more states, for instance, in a certain energy interval, well, indeed, for an atom would be more three-dimensional. So there are perhaps less states close to here than close to there, all right? And this changes the rate. So this is, grossly speaking, what you would need to do to calculate rates to a continuum. For a single discrete level, there is no problem, except for allowing some broadening. For a continuum, there is a density of state problem that has to be taken care of. Okay? Other questions? Okay, so let me start now discussing many particle systems. I will try to give you an overview of what is the problem, what is the solution of this identical particle problem, what physics requires for the wave functions to respect, and also do some application. For instance, we'll try to calculate the spectrum, or at least the ground state of helium. Helium is a two-electron system. In some sense, it's closely related to a nitrogen molecule, except that the centers of the two atoms are now coincident in some sense. I mean, the nucleus themselves has charge 2. The physics is, however, very different from that of a nitrogen molecule. Okay? Indeed, a nitrogen molecule is a kind of complicated problem to deal with, while helium is relatively simpler, and we will try to do estimates of the ground state energy, which in the end are quite good. Generally speaking, when you have more than one electron, the complication of your calculation will really exponentially in the number of particles be enlarged, okay? So calculation with one electron often require using a computer if you have no exact solution available, but the type of numerical calculations that you have to do, so solving the Schrödinger equation for a single particle in a certain three-dimensional potential, is numerically affordable in many cases. You can do quite sophisticated calculation. But if I ask you to do the same thing for a system of, say, 4 interacting particles, 5 interacting particles, not to mention the 10 to the 23 interacting particles that you have in a piece of material, the life becomes a mess, okay? So you have to invent immediately approximate techniques to deal with those systems. 2 electrons are still on the verge of things that can be done. Quantum chemists are obviously masters in calculating this thing, because typically what you have when you have a small molecule, you would like to calculate effectively the Schrödinger problem with a few electrons and see what are the levels, okay? And a quantum chemist typically knows how to set up a numerical calculation to calculate those numbers effectively. But that's a very complicated business. Okay, so let us start from scratch. So until now, if I have a single particle, just one, I have a Hilbert space of a single particle, which I know is made really of 2 parts. It's an orbital part times a spin part, okay? We have discussed at length this thing. So suppose that I have a certain basis of this object, so I have some labels. In the past, I was using N to label things, okay? Now, let me be even more abstract. I will call alpha, alpha a basis set of this object, the orbital Hilbert space, okay? And obviously, for the spin, say, suppose that I have a spin 1/2 particle, then the Hilbert space is generated by the state plus 1/2 and the state minus 1/2 along, say, Z, for instance. This is a basis, then you can, okay, good. Now, you know that a basis for the combined state is simply putting together this with any of these 2 things, okay? So for instance, let me just say that I have a state, alpha, which is made of some orbital part and some spin part, okay? Well, rather than indicating the Z, let me just remind us that this is the spin part, okay? Well, I know that it's along Z, but it's good to remember that this is spin and this is orbital. And I have to decide which one. For instance, let me say that there is a certain sigma, and a sigma associated to this alpha. Could be plus or minus, okay? Good. The notation is a bit probably not particularly nice. You might say, okay, here alpha is a label for the full state. Here alpha is the same label, but for the orbital. Obviously, let me indicate this with the underline to mean that this is a part of the label specifying all the orbital part, and this is a part of the label specifying what the spin is, all right? So really the label is made of many pieces, 2 pieces. The orbit, for instance, okay, I might have here alpha, and here I might have N, L, M, okay, and either, for instance, either plus 1/2 or minus 1/2, okay? This is a possibility where now I'm using for the orbital part hydrogen-like orbitals. But this might be a useful basis to describe many hydrogen atoms, for instance, so many particles in an atom. But if I was discussing many electrons in vacuum, for instance, then maybe a better basis would be plane waves, okay? So this would be things like K for the orbital part, and again a certain spin, sigma alpha, okay? So alpha in some sense is a collective label to mean some labels for the orbital part and the label for the spin part, all right? Which could be, is this clear? So don't let you be confused by the fact that sometimes the same symbol or almost the same symbol appears here and there. It's simply a multi-part object. In the same spirit, for instance, I might use position basis. Now, you remember a position, the position eigen the cat, okay? It's a rather singular object. You remember, it's a delta function, essentially, in a certain point, r, and spin, okay? Again, this is also a possible object. Now, this thing, I will just briefly indicate it by r. So whenever I don't put the arrow on the r, it means really a multi-part label which is made of the position and the spin of the particle, okay? So this is for a convenient notation. With that, okay, when I indicate psi alpha of r without arrows, what I mean is the following. I mean essentially the overlap between the orbital part r and the orbital part of alpha and the orbital part, whatever is the sigma that you have there, okay, and the orbital part of sigma alpha, okay? So alpha has a certain orbital part, alpha underline, and a certain sigma alpha, and r as well has a certain position r and a certain spin part of the label alpha, okay? So this is the wave function. Therefore, to be complete, this is certain function, okay, alpha of r, times what? Well, I might indicate it in several ways. For instance, in analogy to this, I might indicate it as chi. So I need here down the index of the object, so chi sigma alpha, and here the index of the r, so sigma. Okay? It's a very, this notation is to indicate a very simple object. How much is this? This is simply the delta of sigma and sigma alpha. Okay? I mean, a very trivial object. But in order to make it very similar to the wave function, okay, I give him a notation that is pretty similar to that. Okay? So there is a label for the spin associated to the state alpha, and the label for the spin associated to the position. Okay? All right. In this way, I can, with one single object, psi of alpha and r, really indicate orbital and spin part of a wave function altogether. All right? This is the only reason why I introduce this object. Because otherwise, every time I write a single state, I should specify there is an orbit and there is a spin. Okay? When I write from now on an object like this, I mean product of those two things, and therefore, in one shot, I indicate orbital and spin. All right? Good. Okay. For a single particle, I mean, we have done several things, and therefore there is no need to really revisit in some sense. You know that you can choose many orthonormal bases for instance, for the orbital part. The spin is very, very simple. Even in that case, however, you can combine states, and you can, okay? All right. Now, what about a set of n identical particles? okay? So I now have really n identical particles. If the particles are not identical, by the way, then there is nothing particular. It's pretty much like here. So you, again, take the Hilbert space of the first particle. Let me indicate the Hilbert space of the first particle by H1, okay? So this would be, for instance, H1, okay? It's a product of orbital and spin, but it's a Hilbert particle of first particle. Then there is a Hilbert space of the second particle, a Hilbert space of the third particle, and so on, a Hilbert space of the particle number n, okay? And one would say, okay, exactly as I do there, I do products, orbital and spin, and I will do products of 1, 2, 3, and 4, okay? So the most obvious objects that you can think are here an arbitrary state will be alpha 1, okay? I indicate just alpha 1. What I mean is there is an orbital part and the spin part, okay? But in one shot, I make both. Then I would have a certain, another alpha for particle 2, okay? With the same type of choice, obviously. Don't change type of basis from one particle to the other. So if I decide for hydrogen-like orbitals, let's use hydrogen for everybody, not hydrogen for particle 1 and K for particle 2 and whatever, okay? So once you select a basis, call it alpha, be consistent. But the element of the basis that I select for particle 1 and particle 2 might be very different, okay? And I can continue here. Particle 3, in general, will have another element, and particle n will have another element. This is a product of states in the different Hilbert spaces. Well, you might say, okay, this is the building blocks, then I can sum several of these, and this will make a nice state. Almost, okay? If the particle were indeed distinguishable particle, different particles, then this would be a good way of reasoning in some sense. But if the particles are identical, this is not correct. Now, first of all, let me just give you exactly like here. You see, here in some sense what I did was to take the overlap between R, the state ket of position and spin, and alpha, the state ket of a certain label and a certain spin label. All right? Now, in the same spirit, I can take now the overlap between, say, this with R1, R2, Rn. Okay? Obviously, every particle looks only at its own friend on the left. For instance, this looks at that. All right? One looks at one. Okay? So the overlaps are only between particles in the same Hilbert space, okay? However, it's impossible to find a notation in which, I mean, this matching is, I mean, I could write, for instance, R1 here and Rn there, but certainly you have always to remember that it's simpler if you look at the numbers, okay? The numbers will be always associated to a certain Hilbert space number, 1, 2, 3, and so on, okay? So this function here, this product function, is indeed written in terms of wave function, psi alpha 1 R1, psi alpha 2 R2, psi alpha n Rn. Is this clear? Okay? Where I should stress again that this is already a product of orbital and spin part. Orbital and spin. Okay? But n of them multiplied. So this is the simplest state you can think of. Product state. You might say, okay, I'm now ready to go on. Several of them. Well, wait a second, and you will see that this is not quite the whole story. Consider, for simplicity, n equal to 2, okay? So only two identical particles. Okay, let's think a little bit more about this. Then obviously I have a certain Hamiltonian. Okay, the Hamiltonian might be P1 square over 2m plus a certain potential, for instance, like this. Then I should have P2 square over 2m plus a certain potential, plus some interaction, V interaction, R1, R2. Now, in the way I wrote this Hamiltonian, already I made several assumptions that are all justified by the fact that the particles are identical. For instance, you see the masses are identical, obviously. Otherwise, in general, I should put M1 and M2 there. No, I put M because they are identical particles. The potentials that each of them feels independently, they're also identical functions, you see? Obviously, if the particles were not identical, then in general they might feel different potentials. But they are identical, and therefore they must feel the same potential. Okay, also the interaction is such that since the two particles are identical, this thing is totally insensitive. If I write like that, this should be the same function if I just exchange the two labels, right? For instance, this might be some Coulomb interaction, like E squared over R1 minus R2. It doesn't care about if you calculate R1 minus R2 or R2 minus R1. It's just the distance between the two identical objects, okay? So one thing, so let me write this as the Hamiltonian of 1 and 2. You realize immediately that the Hamiltonian of 1 and 2 is identical to the Hamiltonian of 2 and 1. In other words, if I exchange all the labels and I consider I exchange 1 with 2, particle 1 with particle 2, this would be P2 squared over 2m plus V R2, P plus P1 squared over 2m plus V of R1 plus interaction between R2 and R1. Same thing, okay? So identical thing. So the Hamiltonian actually allows you to permute the two variables because they don't have a tag on them. I mean, the two are totally indistinguishable objects, and the Hamiltonian is completely okay. So you realize immediately the following thing, that there must be the analog of what we have seen in discussing the parity, okay? Remember, when we had the symmetry of a Hamiltonian that would be even under inversion, okay? So the potential was even. Then there is this parity operation, changing x into minus x. Now I will define a similar thing. Let me call P12 the permutation of operator, okay? So an object that acts in the following way. When it sees a wave function, so for instance a wave function of R1, R2, what we'll do is simply to take the same wave function and exchange the two labels, okay? That's a very well-defined object, okay? It acts on the space of the functions of two variables, and, I mean, functions of two variables are more general than just product of two functions of the two. I mean, just any function of two variables, and it takes the function and exchanges the two things, okay? So this is an operator. Well, obviously this operator is such that if you apply it twice, it's just the identity, okay? You exchange, and then re-exchange, you get back to the origin. Very trivial thing. Now you see, this is an operator. His square is 1, and it's very simple to prove that indeed it commutes with the Hamiltonian. In other words, P12 H is equal to H P12. Very simple. You just apply this to the to any arbitrary psi, okay? And you will immediately see that, I mean, it's basically due to this fact, okay? So it's pretty much the same proof that we did when we showed that symmetries are objects which, I mean, are associated to operators that commute with the Hamiltonian. If you look at that proof, it's identical proof, okay? So any symmetry will have that property. Okay, now, this means that this operator here, since it commutes with the Hamiltonian, can be diagonalized simultaneously with the Hamiltonian. In some sense, you can find eigenstates of the Hamiltonian that are simultaneously also eigenstates of the permutation, okay? Now, simply the product of two things is not a good eigenstate of permutation, okay? But you can make out of a product a good eigenstate of permutation, actually two good eigenstates of permutation. You can make, for instance, an even function, okay? Psi even of R1 and R2. How do you make it? Okay? Well, for instance, suppose that you have some, let me call a psi A R1 and psi B R2. Okay? I'm making the notation a bit. I'm calling this A and this B. Okay? Just to make it a bit quicker. Now, how do I make an even function by taking psi A of R1 and psi B of R2? Well, simple. Let me try to exchange these two. I would have here psi A of R2 and psi B of R1. I simply taking the same two functions but exchanges the two variables, okay? Now I want something that is even when I exchange. Well, then I just put a factor plus in here, and if I really want, I put a 1 over square root of 2, so that if the two functions are orthogonal normalized, this would be also nicely normalized. Okay? Is this clear? This object here is for sure a eigenstate of P12. Just check P12 of psi even, written in that way, okay, is, okay, by definition is equal to psi would be psi even R2, R1, but if you try and exchange R2 and R1, you notice you obtain the same thing. So this is equal to plus psi even R1, R2, okay? So be careful. This is the definition of P. This would apply to any function psi. The fact that this is equal to its partner with the variables exchanged is, I mean, is a peculiar thing of this function here. And therefore, this immediately tells you that this is an eigenstate with eigenvalue plus 1. Okay? So, well, you know that since p squared is 1, the only two possible eigenstates are plus 1 and minus 1. So, plus 1 we have found, for instance, the even states. Now, how do you construct an odd state? An odd under parity, okay? So an anti-symmetric state. This is also called symmetric. Now let me construct an odd or anti-symmetric. It's the same thing, okay? How do I do it? Okay, when you exchange now, this thing becomes that, and this thing becomes that, but they have a minus sign difference, and therefore the odd case, which is still defined in the same thing, however, acquires a minus sign here. Okay? So it is clear this is kind of guiding us. In distinguishable particle, we'll have Hamiltonians that do not depend on the way you permute the particles, and therefore this suggests that the permutation operator of the two particles, which is an operator in the Hilbert space, whose square is 1, it should be possible to diagonalize it simultaneously with the Hamiltonian, and therefore the good states that perhaps you have to consider are symmetric or anti-symmetric states of that operator. Now, this is only a hint, obviously. Then there is a theorem that that particle theorists in particular have expressed. It's called the spin statistics theorem. And it tells that essentially the only possibility that nature allows is the following. When you have more than two even indistinguishable particle, you can have only two possibilities. One, the states that are allowed are totally symmetric under any permutation of the two labels. Okay? Here there are only one possible permutation, but if you have more than two particles, you could permute the first two, the second two, the first and the third, the seventh and the 25th. Okay? Now, a totally symmetric state is a state where, I try to write here, a state psi of R1, Rn, such that whatever permutation I do, so for instance, a permutation of 7 and 25, so I take the variable here R7 and the variable here R25, and I just exchange them. Psi R1, R6 remains there, but here I get R25, R7, R8, okay? And in place of R25, I put R7, okay? Just to give you a concrete example. This would be a permutation of 7 and 25, just to tell you, okay? You can do any permutation, and even permutation of more than two pairs, okay? Indeed, let us start growing up a little bit. You know that for every, if you send the set of numbers 1n into P1, Pn, okay, by just scrambling them the way you want, this is a generic permutation P, okay? For instance, just 1, 2, 3 could go, for instance, how many permutations there are of three objects? 6, okay? So the identical permutation, then a permutation in which you exchange 2 and 1, leaving 3 invariant, a permutation where you exchange 3 and 1, leaving 2 invariant, a permutation where you exchange 2 and 3, leaving 1 invariant, and then give me the other two. I, for instance, 2, 3, 1, okay? So 1 goes into 2, 2 into 3, and 3 into 1, the cyclic one, and finally the anti-cyclic one, where 1 goes into 3, 2 goes into 1, and 3 goes into 2, okay? So these are the 6 possible things. For n factorial, large number, okay? For any of those permutations, okay, a totally antisymmetric state would be totally insensitive, totally symmetric, sorry. Okay? It would be exactly the thing. For any p in the list, p of psi R1, Rn, which is nothing but psi of R P1, Rpn, is totally identical to psi of R1, Rn. You realize this is a very strong thing, okay? So you scramble the variables in the functions. In any permutation you can come to your mind, and the function is still the same, okay? So you see, it happens. Okay, for instance, we have constructed here. But, I mean, they're not generic functions. They're very, very sophisticated and peculiar functions, okay? Those are allowed, and they are allowed for system of bosons. So particles that have a spin which is integer spin. Spin 0, spin 1, spin 2, and so on. For instance, one notable important physical case of a system of bosonic particles. Helium atoms, okay? You might object. Helium-4. There are two species of helium, helium-4 and helium-3. They differ by a subtle thing, which is the nucleus. They have always 2 electrons, but the nucleus is slightly different. The nucleus of helium-4 is a standard nucleus with 2 with obviously 2, both have 2 protons, but they have a number of neutrons, I think it's 2, okay? The total number of, I mean, both electrons, neutrons and protons are fermionic objects. They have spin 1/2, okay? But by putting themselves together, they can form integer type of spins, okay? So in some sense, helium-4 is a composite particle, made of objects that are half integer spins, but in a way that if you look at it studying certain properties like superfluidity or things like this, I mean, condensed matter type of energies, they look as objects that you cannot break, okay? To break the atom, you should ionize it and do higher energy things, okay? So to low energy, they behave as individual objects, and as individual objects, they behave like bosons, okay? So in some sense, to them, so if you describe by R1, R2, just the position of the whole atom, not the individual electron inside and the individual proton, the whole atom, they would behave like bosons, and they would require totally symmetric wave function, okay? Helium-3 differs by a neutron, okay? So something very, very irrelevant to us. I mean, the charge is the same, 2 electrons, 2 protons. However, the spin the object has in its belly a spin that is different now. It cannot be an integer because it's an odd number of half-integer particles, and therefore it becomes a fermion. And the fermions do something totally different. They do the following. They do something similar to this generalized, which I now write here. So for a system of fermions, identical fermions, obviously, if you take any permutation P, you apply to the wave function, this obviously will give you always the same object, Rp1, Rpn, but the system is totally antisymmetric if this thing is also equal to -1 to a number that I will tell you in a second, times the original one. Okay? So in some sense, this thing was simpler. There was no sign whatsoever. Now, there is sometimes a plus and sometimes a minus. Now, what distinguishes if a certain permutation is a plus or as a minus? It's a property of the permutation itself. It's somehow a characteristic of the permutation. It's the number of transpositions that you need to make to get it, okay? For instance, let's see. To get from here to here, no transposition, okay? To get from here to here, well, you just make a transposition of 2 and 1, okay? So in some sense, this would be 1 transposition. Okay? In that case, -1 to the p is just -1. In the first case, -1 to the p, since you need no transposition, is just +1. Let's see this one. This also needs a single transposition, 1 and 3. So this would be also -1. This needs a transposition, 2 and 3, so -1. What about this? Well, this needs, for instance, it can be obtained in many ways. For instance, you could start exchanging 2 and 1, okay? And getting 2, 1, and 3. Then you exchange this 2 again to obtain this, okay? So you see immediately that you need 2 steps of transpositions, and therefore the number of transposition is an even number now. And therefore this has +1. Let's see the remaining one here. Again, for instance, you can start from here and let me see. You can, for instance, yes, you can take from here and you go to exchanging 3 and 2. You go to 1, 3, and 2. And then the 2 is fixed. And then you do an extra step by exchanging this 2, and you go to 3 to 1. So again, 2 transposition bring you to this permutation, and therefore the sign is +1. Okay? So the sign that you have to put here is P, which is equal to the number of transposition which make the permutation. Okay? Now you might object, but is it unique, this number? No. It's not unique, but the parity is unique. Okay? So you can go from a certain, you can go to a given permutation, in general, in more than one way. And sometimes these 2 ways have a different number of transpositions, but be guaranteed by studying the theory of permutations that the number of the parity of the number of transposition is the same. Okay? So even if the route that you do to get from 1 to the final, in this case was only 3, and there are not many routes that you can make. Okay? But when you have more than 3, you can play around a little bit. You will see that there are several ways, but those several ways will have the same parity. So the number of transposition is a characteristic of the permutation itself that you have performed, and not of the route that you use to get from the initial configuration to the final. Okay? So this number, which is a bit tricky in general, I mean, given a permutation you have to start counting, is the sign that you have to put in front of the wave function for fermions. Okay? So in some sense, bosons are less requiring. They just are happy with the plus. Fermions are a bit tricky, and they want either plus or minus, depending on the parity of the transpositions that you have to make. All right? Now, these are the 2 only physically meaningful cases. Okay? Any other function should be banned. Okay? So this is a very, very stringent requirement. Now, if you go back to our simple products, you see that many of them are just impossible. Actually, a single product will never be, except in very, very special cases. For instance, if all those labels are exactly the same, then obviously this is a good function for a bosonic system, because you exchange any label and the function will be exactly the same. All right? But this is a very special case. As you start, for instance, by having labels that are different, alpha 1 and alpha 2 and alpha n different, then obviously a single product will never be able to realize any of those 2 stringent requirements. Okay? So we have to start summing products, okay, in order to make the functions physical. The single products are unphysical. The appropriate sums will be physical, but we have to learn how to do that. Okay? So for a case of 2, it was very simple. We just just sum with the reversed one, or take the difference with the reversed one, and you construct the good physical states, the even and the odd. But if you have 3, 4, 5, things start becoming a little bit more clumsy. Okay, so how is this done more in general? Let's see. So hopefully it's clear. Okay, let me summarize. This is going to be, I mean, full of many little things that perhaps is the first time you see it in some detail. So I want to make sure that you follow me, at least this time. Okay? Now, a single particle, several particles, a product wave function. Then we discussed that these are not good in general. Okay? So for 2, the solution was simple. Symmetric and antisymmetric functions can be simply defined given any 2 product function. In general, physics requires for bosons a totally symmetric and for fermions a totally antisymmetric function, which means that when you permute the labels, the function with the labels permuted should be equal up to a sign to the function with the unpermuted labels. All right? This is what we want to learn how to construct now. And I will tell you in 5 minutes how to construct this thing. Okay, so if the goal is clear, let me start defining what we need. Perhaps I should. Let me see. Okay. Good. So I start again from here, a product state. Let me make it shorter notation. Alpha 1, alpha n, okay? Never mind. I don't want to introduce too many notations, otherwise, I mean. So this is a product state. Now, when I take a permutation of a product state, now I should distinguish really permutation as a mathematical object of, I mean, just permuting numbers. So for instance, this is permutation, with the corresponding operator that you can construct on the product state, okay? So I try to use a fat P to mean the operator that works on the Hilbert space and implements exactly a given permutation. A permutation of what? Of the labels, obviously. So this object is nothing but, by definition, takes the alpha and the first state, and rather than putting in, so this is first state 1 and this is state n. Rather than keeping it in state alpha 1, it puts it in state alpha p1. Okay? The 2, okay, will be in state alpha p2. And the n, finally, will be in alpha pn. Okay? Is this clear? So this is the index of the Hilbert space, and therefore tells me, okay, which particle I'm considering. And this is the new label, okay, which is one of the labels that was previously present, but maybe is the label that, I don't know, electron 3 before had. Okay? Is this clear? To be concrete, imagine that you have 3 electrons, and I tell you that there is an electron in the ground state of the hydrogen. So 1, 0, 0 with, I don't know, spin up. And another electron is in the 2s, 2, 0, 0 with spin, I don't know, down. And another is in the, I don't know, 3p. So 3, 1, say +1, and spin up. Okay? Now, these are the 3 states, the 3 labels present. But there is really no way of saying that this electron has a tag on it with written 1, okay, in, say, red ink on the electron. And here there is written 2, okay? So in some sense, I started by writing that there is a state for electron 1, which is this 1, 0, 0, 0 up, and the state for 2 that was 2, 0, 0 down, and the state for 3 that is 3, 1, 1, 1 plus 1 up. But now I allow myself to, for instance, permute the labels and say, hey, no, Mr. 1 is also a candidate to having, for instance, the label of the 2. So 2, 0, 0 down now goes with 1. And, for instance, 2 gets 1, 0, 0 up. Okay, and 3 remains there. 3, 1, 1, up. Okay, so I can start playing with permutations. Okay, so fixing the labels that are presented in the state, alpha 1, alpha n, so the ones that I want occupied, I start having them exchange the shirts in some sense, okay? So the shirt with the tag 1 is given to electron number 2 and so forth, okay? Is this clear? Okay. So this is what the permutation does on the states. It creates new states, which are closely related to the other ones, so they are still product state, but now with the labels just scrambled, permuted, okay? This is something that you can certainly easily define. Okay, now, let's see. Out of this object, I can now define the following object. Alpha 1, alpha n, some overall permutations, okay? So not just one, but all of them. Let me put here, what? Well, let me put this, two possibilities. For the bosons, just a +1. For the electrons, a -1 to the p. So for the fermions, a -1 to the p. And then I do p, the fat p, applied to the state alpha 1, alpha n. Now, this object, we have just rewritten what it is, okay? So I could also re-express as alpha p1, alpha pn. Okay? So it's the product with the labels exchanged according to the permutation. Now I sum overall the permutation, all right? And I do the sum with the following thing. If I do it with all +1s, I'm trying to construct this type of states. If I do it with -1 to the p, I'm trying to construct this. I have to prove it to you, obviously, okay? So, but believe me, we will prove that these two possibilities, okay, will indeed, in the end, result in functions that are either totally symmetric or antisymmetric in the way fermions would like, okay? So they are a way of taking products and creating some of them in the appropriate way that the resulting object is allowed, okay, physically good. So this is the generalization of what we did before with 2. Remember, we had psi A and psi B. What should I do to construct an even and an odd? Just sum with the reverse one or subtract the reverse one, okay? In that case, there is only one permutation really to take care of. Identical and the one that exchanges, okay? Now I'm generalizing that construction to an arbitrary n, okay? So the number of terms that you have to consider now is much larger, n factorial, not just 2. All right? But this object, one can prove, is nice. It's totally symmetric or antisymmetric. Okay? Shall we adventure in this proof? Okay. It's not difficult. By the way, I'm using a slightly different notation from here. Here, I'm writing this as wave functions, okay? Here, I'm writing it as abstract ket. There is a way of going from here to here. In other words, if I take this and I multiply by R1, okay, R2, Rn, exactly as we did here, then I would obtain, in general, psi of alpha 1, alpha n, R1, Rn. Okay? And my claim is that this object is either totally symmetric or totally antisymmetric, depending on what I use here. Okay? In order to make this more kind of common to both, let me write it as psi to the p. Okay? Psi would be +1 for bosons and -1 for bosons, for fermions. Okay? In other words, if I take the power, the +1 to the number of transposition, always remains a +1, okay? while if I take -1 to the number of transposition, is the appropriate number for the fermions, okay? So I can combine them into a single thing where psi, however, is +1 or -1. Okay, so the proof of this is not complicated. Well, it's indeed supposed to be an exercise in the notes, but let us try to do it at least. I mean, understand why. Okay. All you have to prove, in some sense, is that. So let us work with the cats. If you allow me, I work at this stage here. I want the following thing. Suppose that maybe I should get rid of some of this. Suppose that I apply a given permutation. Remember, as an operator on the state, I make it a bit fat. To this state here, alpha 1, alpha n. Okay? Well, what does it mean? According to the definition I gave, it must mean that this is just the ket that I would obtain if instead of starting from alpha 1, alpha n, I start from alpha p1, alpha pn. Okay? So I do the same procedure, but now starting with the labels already scrambled from the beginning, okay, with a given permutation. But now the procedure, the way I define this ket is that I have to sum over all permutations, okay? So you realize that by summing over all possible permutation, in some sense, I must use properties of the permutation themselves, okay? So if you combine two permutations, you obtain another permutation. They form a group, okay? And if I have a permutation P times any other permutation, say P tilde, okay? Let me call P tilde the permutations that appear there in the sum. Well, I obtain another permutation. But summing over all possible P tilde is obviously the same thing as summing over all possible PP tilde. Okay? In some sense, it's like changing variables in an integral. PP tilde will run over all possible permutation in a one-to-one way. Okay? Because if two P tilde are different, then the two PP tilde will be different, and therefore it's pretty much the same way of performing the sum. Maybe I should clarify this a little bit more. Yes, this is, it has to do with group theory, and therefore, strictly speaking, is something that should go into some other room. But let's try to make it somehow. Let's try to make it reasonable for a physicist. Okay. So what I mean is the following. For instance, let's do the example of 3. Okay. We have the table here, and it's much simpler. Suppose that I want to sum over all this 6 permutation there. But now I put an extra permutation in front of everything, right? So I put, for instance, this permutation, 2 and 1, okay? So I want this to be the transposition of the first 2 elements, but then I have to sum, according to my thing, over all permutations again. Now, you realize that if I first transpose 2 and 1, and then I want to permute all the indices in all possible ways, it's quite the same thing than just permuting all the indices in all possible ways, right? So I transpose 2 and 1, but then I don't care. I permute all possible things. Why did you transpose 2 and 1? Just permute, and that's it, okay? So is it clear? I mean, putting an extra permutation in front of all possible permutation is not really much more than just doing all possible permutation. There is only one point, is the number of transpositions that you are taking care of. I mean, this number is not important for boson, but it's important for fermions, okay? So in some sense, if you put in front of all the possible permutation an extra permutation, you are inserting an extra number of transpositions, okay? So in some sense, the two things are the same, but they differ by a possible minus sign, okay? So this is exactly the possible minus sign. So in other words, this object here is equal to, for bosons, is just equal to plus alpha 1, alpha n, okay, itself. And for fermions is minus 1 to the p alpha 1 alpha n, okay? So let me try to comfort you again. Now, each of those objects, this, and this, should be constructed in this way. So you should take the label, sum over all possible permutation of the labels, putting possibly plus or minus sign, okay? However, if I pretend to insert an extra permutation in front, then what I'm doing is still summing over all possible permutation, just with a different initial, say, permutation. And therefore, the result is totally identical, apart from possibly a number of transpositions that I have to allow, okay? Perhaps the best thing for you is to do yourself the case of 3 in a very explicit way. I don't think we have enough time to really do everything in so much detail, but let's try to, okay? At least set up what is the thing that one should do, for instance, for 3, okay? Since I want to go very slowly in this part, I think it's a good exercise, okay? So let me just start doing simple things. So for instance, suppose that you have 3 particles, okay? And now you have, therefore, 3 states, alpha 1, alpha 2, and alpha 3. Okay? And, well, perhaps you will allow me to call this A, this B, and this C. Okay? It's a bit quicker. Since they will be just exchanged by all of them, it's not important to call the first 1, the first 2, and the first 3. It's only the initial choice, but then you have to scramble them. So let's call that just A, B, and C. Okay? So the equivalent would be here. Let's see. The state A, B, and C. What will it be? Okay? Well, will it be, well, obviously, a scalar product, so scalar product with R1, R2, and R3. So this would be the identical permutation will always give me psi A, R1, psi B, R2, psi C, R3. Okay? So the initial choice. Okay? Good. So this in the end will be the function of A, B, and C associated to R1, R2, R3. Let's see. Let's put a plus. So let me select, for instance, so no, let's go in the order. So here, the identical permutation is a plus. Okay, good. The next one, which one is it? Is the transposition of 2 and 1. Okay, good. So what I should do, and it has a minus for the fermions, obviously a plus for the bosons. So I put just both of them in that way. Okay, so I now transpose the label of 2 and 1. So I write, for instance, psi b of R1 and psi a of R2. Okay? So now particle 1 is, rather than in A, it's in B. And particle 2 is in A rather than B. Okay? Particle 3 stays in the same. Okay? Let's go on. The next one is this. Now 2 stays fixed and 1 and 3 are exchanged. Okay? So what I do is I have a plus for the bosons and minus for the fermions. Psi, okay, so 1 goes into the 3, so the C. 2 stays fixed, so remains in its own initial B. And 3 gets the one of 1, so A. Okay? Now I go on. I've done this, I've done this, I've done this. 1 stays fixed, and 3 and 2 exchange their label. So again, plus or minus. So 1 remains in A, and 2 gets C, and 3 gets B. Okay? And I have done 4 of them. And now I have the cyclic and the anticyclic permutation. So let me, well, maybe I should write it downstairs here. Plus, they both have a plus. Okay? So the 1 gets the 2, so B. The 2 gets the 3, so C. And the 3 gets the, what I've done here, 1 gets the 2B, 2 gets the 3C, and 3 gets the 1A. And the other is the opposite. So 1 gets the 3, so C, 2 gets the 1, so A, and 3 gets the 2, so B. Okay? Hopefully, this is straightforward. Okay? So I have 6 permutations for 3 objects, and I have to take the initial product state, okay, and together with the initial one, I should sum over all possible scrambling of the labels with permutations, including, for bosons, always a plus sign, for fermions, sometimes a minus if the corresponding permutation involves an odd number of transpositions. All right? So this is the final result. It's a sum of product states. The statement is that this is, for the case of plus, totally symmetric. Let's verify. Okay? So this is the statement that I was doing here. Okay? It's a fancy way of saying that if you take now this function and you, for instance, permute, I don't know, 1 and 2, I should get plus always. Well, it's very simple. You see, suppose that I can do the permutation on the labels or on the variables. It's exactly identical. Now you see, for instance, if you permute the variable 2 with 1, you get psi A R2, psi B R1 in this term. Okay? Well, if you go somewhere, you will find that that term, okay, so for instance, for this term, you will get psi A R2, psi B R1. I'm permuting this 2. Good. But you see that I have that term. It's there. It's just written in an opposite order, but these are product things. Okay? So this term is there. Okay? Then I take this, and I permute 1 and 2, and I mean, obviously, you will notice that I have that term. It's there. Okay? And so forth. I can do it for any possible term, and I will really catch for every term a corresponding one that has exactly the same form, and all with the same plus. And therefore, the result is that this function, okay, if I apply the permutation of 1 and 2, is exactly identical. And you can prove that any permutation that you can think of since I am here summing over all possible permutations, will be still totally present, okay? And therefore, there is nothing else but a totally symmetric scrambling of the thing, all right? On the contrary, if I do, for instance, a permutation of, let's do the fermion case, a permutation of R1 and R2, well, then you notice that here you get this. But for instance, from this term, which has now a minus sign in front, you get psi B R2, psi A R1. You notice that this is exactly the same you have here, just written in the opposite order, but this is supposed to go with the minus, while this was with the plus. And therefore, when you do the permutation, this gets the place of that, but with the, the opposite sign, and this goes with the place of that, with the opposite sign, okay? And you can see that also the other pieces, okay, have corresponding minus signs in front, okay? So the result is that for fermions, if I do the permutation of 1 and 2, you will get, by definition, R2, R1, but this thing is equal to minus psi A, B, C, R1, R2, R3. Okay? So please verify that all permutations that you can think work out exactly as they should. And this is, therefore, a general way. So this sum over all permutation of sums times the permutation is a general way of doing what we did just by looking at the thing for n equal to. Okay? Remember, we constructed even odd by just writing it. Now we found a more systematic approach, which involves a sum over all permutation. You realize how cumbersome this is. 3 particles, 6 terms. 4 particles, 6 by 4 is 24 terms, okay? Half a blackboard. 5? 120 is our calculator of factorials. Good. 120. You realize, right? I start studying a system of 8 particles, and I would need to write wave functions along several pages by just including all possible permutations. What a mess. Now, second quantization, which is not something that we'll do, probably last lecture I will discuss, if I have time, is a way of keeping track of all this, signs, of all these permutations in a very quick manner, okay? In some sense, what is important, that I told you here to construct those states, is what labels I have used, right? The choice of the initial A, B, and C are important, because the rest is just a democratic way of exchanging the shirts, okay? Nothing else. So it's really an exercise of permutation theory. What is really making this state different from another state is what A, what B, and what C I selected, okay? And how many times A, B, or C happen to occur. For instance, if 2 of them are the same, or things like this, okay? So second quantization allows you to simplify enormously this n factorial business into an effective way of counting things, okay? But for the time being, I want you to, test the crude reality of what does it mean, in principle, to implement this requirement of total symmetry, of total anti-symmetry, even into a simple product type of state. Okay? It means summing a lot of numbers. Now, I want to end up this lecture with a single observation now, or maybe 2 connected. First, you will realize pretty simply that the antisymmetric choice makes a very simple construction. Let us try to do it. if I have as a starting thing this object, and I want now to sum over all possible permutations applied to this thing with -1 to the p. What is it? Well, according to the way this is defined, is the sum over all possible permutation of -1 to the p. Well, remember I have to take the first and put it in p1, p alpha 1, alpha p1. The second and putting in alpha p2. And the last one and put it in alpha pn. Okay? Can you tell me what this is? Wait a second before you answer. Suppose that I have a matrix, okay? A. This matrix is A11, A12, A1n, AN1, AN2, ANN. Okay? So matrix Aij. The determinant of A. You remember how to calculate it? There is a way of calculating it with the sum over all possible permutations, -1 to the number of permutations, and then you put, for instance, A P1, 1, A P2, 2, A Pn, n. Okay? In other words, take an element from the first column, element P1, second column, element P2, third column, P3, n column, Pn, okay? Where P1, P2, Pn will be all different, obviously, and make a product, okay? Then start again, another permutation, and include a certain sign, plus or minus, okay? So this thing makes a determinant. But now if you look more closely, they're quite the same thing, right? If I make a matrix, which is psi alpha 1 R1, psi, for instance, let's see, I think that I'm making here alpha 1 Rn, psi alpha 2 R1, psi alpha 2 Rn, psi alpha n R1, psi alpha n Rn. Okay? Take this matrix with the functions you selected and take the determinant of it. And you see that immediately you get this. Okay? That's the reason why these are called Slater determinants. Remind you, it's nothing but what I wrote here. It's just written in terms of wave function rather than abstract cats, okay? It's the same thing. Sum over permutation of the permuted product with the appropriate sign. All right? It's the same thing. But now you can give an interpretation a bit more matrix-like. By the way, if you try to write a 3x3 matrix, in this case, and you calculate the determinant of the 3x3 matrix, you will get these 6 terms with the minus signs where they are. Okay? For the bosons, rather than a determinant, you will get what is called a permanent, not a determinant. So the permanent has +1. It looks simpler, but it's in fact more complicated to calculate, for instance, on a computer. Okay? You really have to sum over all permutations. It's a mess. The determinant, there are tricks to calculate it because, after all, I mean, you can diagonalize matrices, calculate things in a simpler way. So there are effective ways of calculating determinants of matrices, while the permanent is a mess. Okay? Close the parenthesis. I don't want to. This is just to tell you that there are large numbers, as you would expect in a determinant of a matrix. Okay? final remark, and then we go. Pauli principle. If I happen to choose two of these labels to be the same for a system of fermions, what happens? Well, there are two ways of noticing that what you get is zero. You do not get a state, you get zero. One way is the following. If alpha 1, for instance, and alpha 2 are the same, this matrix here has the first two rows identical. Okay? And you know that when a matrix has any two rows, in fact, or any two columns that are identical, then the determinant is 0. Okay? So, if you choose two labels in the product state that are identical, any two labels, the resulting totally anti-symmetrized product state that you should construct to be physical is just vanishing. Okay? So you cannot do that. So Pauli principle forbids that alpha I be equal to an alpha j. Okay? So the alpha 1, alpha n that you select there, they must all be different. Not necessarily all be different by, for instance, orbital number, but at least the spin has to be different. So, okay? So for instance, you can select the same orbital with a given spin and then the same orbital with a different spin. Okay? So at least some part of the label has to be different. Okay? So this is one way to notice the Pauli principle. The other way is just noticing that, for instance, if you do a permutation, you should get a minus sign, but if you permute two things that are totally identical, you get no change of sign. So the only state, I will do that next time even, I mean, more detail, okay? But I want to leave you with this thing that Pauli principle is already in this way of constructing the state. Yeah. No. The bosons can be all in the same thing. In fact, we said, if alpha 1 and alpha n are all the same, this is a bosonic state, totally allowed. Okay? Not allowed for fermions. Yeah.
Does the determinant have any physical meaning? Slater determinant.
You always ask difficult questions. You should ask Slater maybe what he had in mind. I mean, in some sense, you see, it's a mathematical tool that has to do with the fact that permutations work always the same way in different contexts. I mean, physically, what is important is a certain property under a permutation of labels, okay? And it happens so that the determinant have the right property that fermions would like to have. What is very deeply behind this, probably, I don't know, a good particle physicist should be inquired. I don't know, Salam, but yes, he cannot answer now. So there must be probably some very, very, very deep reasoning behind, but let me omit any attempt of giving it. Okay, so I'll see you next week.